Uh-huh. Okay, so yeah, this is a testable question. There's nothing wrong with this one. Um, Anything in this range. The only thing is, yeah, these questions start getting more complicated when you start bringing together both the incline and the concept of perhaps a coefficient of friction. That's when we start seeing these problems get, you know, I think you guys would say the word hard. I would say they just become, um, overly complicated. If your goal here is to try and teach what's happening and to try and give you a sense of appreciation for the physics part, making it overly complicated, I think, obscures your ability to know what's really happening. That doesn't mean that you couldn't be given a question like this and then asked to discuss the frictional force. To make it a problem where you have to have a problem like this and do also the necessary work in calculating how the frictional force might interact with it, that might start to leave the boundaries of what is a reasonable test for AP Physics 1. Does that give you an idea of what I might put on the test with that information? So if not, I see this problem as a reasonable test question if I make the surface frictionless and ask things like the conditions to which the block on the ramp would slide down versus the conditions to which it would slide up. Like how much weight do I have to hang off the edge to get it to slide upwards? This mask is not working, so give me a second. If it falls off my nose again, I'm going to freak out. There we go. Back to this mask. So I think that's a fair and fine question for this one to talk about the conditions where it would slide up or down. Adding friction, if I told you that there was a coefficient of kinetic or static friction here, I don't know that that actually is a reasonable problem to do, not because you're incapable, but I think that I'd probably only get about a 50% return rate on the number of you who'd be able to successfully do it, not because you're incapable of dealing with the coefficient, but because the combination of the coefficient plus the angle plus the trig is a lot of layers there to get the math technically right. So if I was to ask a problem like this, I probably would introduce the concept of the coefficient of friction to see if you could describe how it would affect the problem. Would it allow me to hang more weight off the edge? Or would it let me put less weight before it would start to move? Stuff like that, where you would have to conceptually discuss how adding friction to the problem would affect the problem. Those are the kinds of things that I would probably discuss. Would I make you say, what is the acceleration of the system while having a coefficient of friction and an angle and an outward machine? No, I don't think that's really necessary for the exam. And I don't think that that's a necessary use of your time for the exam, given that the reasonableness of the amount of time we have at 48 minutes, it's hard to put something like that all together on a test question. So homework, on the other hand, sure. There's no reason it can't be in homework. So this one, the block, let's see, M1 is, I have 36. You probably have something else. And my M2 is 19. So instead, I'm going to do this as let's just do 40 and 20 instead of 36 and 19. Everybody okay with that? All right. And they give me an angle of 37 degrees. Do you know why they chose 37 degrees? There's actually a good reason for 37 degrees. All right, you might want to put this in your notes as why teachers do some things that they do. 37 degrees is the angle of a 3, 4, 5 triangle. That means the sine is 0.6 and the cosine is 0.8. So that's why you would use 37 degrees. Or you could probably guess this one. If not 37, what other angle might you use? 53 is the other side of that same triangle. So that's why 37 degrees gets used in physics problems all the time. So if we're going to use 37 degrees, don't jump to your calculator. 37 degrees means the sine of 37 is going to be 0.6, and the cosine of 37 is going to be 0.8. It's a 3, 4, 5 triangle. All right, so you guys learned about the 3, 4, 5 triangles, right? You know what I'm talking about, right? Good. So I don't even know what the problem is about. I would probably say the problem is about acceleration. So let's start there. This is a reasonable test question. So to find the acceleration, I'm going to start by doing all of the set of steps that we have been doing. I had some kids in here yesterday doing some tutoring and stuff, And I get that these can be hard, but I also will throw out some things you should look for in these problems. And you might want to consider on your own time, instead of running the numbers the way we are, actually just working it as M1 and M2. There are some reasons why using M1 and M2 is better than putting the numbers in. Because if you do this problem once, you have done it for every possible Atwood machine that looks like this. And you should know what to expect. So I'm going to do the problem with M1 and M2 and put 20 and 40 in at the end. Okay? That way, when we're done, we've done every one of these questions. And we can see the features that we will expect to see in the answer. Now, you do it however it makes you feel best. I do not know which direction this system is going to go. So you tell me, is the pulley going to go clockwise or counterclockwise? Just pick one. Okay, see, this tells me nothing because I'm on the other side of your clock. So if you go like this, what does that mean? So just say clockwise or counterclockwise. Counterclockwise from my vantage point is this way. So this is our positive direction, okay? That means, and here's where I've seen some students make some mistakes. I am deciding for both masses what direction is positive by that arrow. So if I trace that back to here, that means this way will be positive for this box. And if I trace that over to here, that means this way is going to be positive for this box. This provides a consistent direction for positive and ensures that when we're doing this problem, when we're done, when we get the answer, whatever that is, we know that if the answer comes out to be a positive acceleration, both boxes are going to move in the direction of this arrow. And that's why it's appropriate to pick a common direction. So let's free body diagram this sucker out first. And I'm going to start with a tension. And I'm going to make that tension greater than the weight. If we think the system's going to accelerate upwards, then I need my tension force to be greater than the weight. Look, you guys are great at drawing that picture. That picture is meaningless unless you put down the important details here. The tension is greater than the weight. On the test, I'm asking questions like that. And you need to be able to discuss whether the tension is going to be greater or less than something without having to free body diagram it all the time. You need to have a sense of what it means for the tension to be greater than something or less than something and why. So over here, I'm going to have normal force. I'm going to have weight. And I'm going to have tension. And I'm going to try and draw the tension in such a way that it is the same size as the arrow I have for the blocks that's hanging, because they represent a Newton's third law pair, and they must be the same magnitude. Rachel?
If you were gonna have to explain why the tension was greater, on the other one, would you just be able to say because the system accelerates upwards?
The unbalanced force has to be upwards, yeah. So I've got my free body diagram, and so I'm not going to nitpick all of the steps because you're supposed to be good at this now, but I am going to put a coordinate system in there. I'm going to identify this as my angle theta. I'm going to recognize that I have to wrap a triangle around theta. I'm saying all the steps. I'm not explaining the steps. If you need them explained, you need to stop me and ask. But I'm wrapping a right triangle around theta in such a way that the right angle is on one of the coordinates. I'm drawing this as M2G cosine theta, because that is the component that is into the ramp. And this one is M2G sine theta, because that is the component that is down the ramp. I have drawn my free body diagrams. I have identified all the forces acting on the blocks. I've added a coordinate system. I've taken any off-axis forces and found their components. That leads me to the point where I say net force is equal to MA, because I believe the system is accelerating. So for the box that is hanging, that will be tension minus M1G is equal to M1A. I've reached the end of the road on what Newton's laws can tell me about the box that is hanging. Applying the same idea to the box on the ramp, I will have net force in the x direction equals m2a, and net force in the y direction is equal to 0. In the y direction, I will have normal force minus m2g cosine theta equals 0. In the x direction, I will have m2g sine theta minus tension equals m2a. Now, do your notes tell you the things that have been done there? Because if I just look at this piece of paper, all I see is letters everywhere. Do you have information that tells you where each of those things came from? Do you have enough guidance so that when you are studying this evening, you can recreate what is necessary for the test? Because Thursday, you'll have to do this without a net. You'll have to be able to pull it from your mind. Now, I didn't need the y direction. There's no friction. It should not be coming as a shock anymore that friction is highly dependent on a normal force. It is proportional to the normal force. If there's no friction, generally, the normal force doesn't play a prominent role in your problem, unless, of course, your normal force is doing something else. But in this case, it's not. But you should always be aware that if there's going to be friction, you're going to need to know about the normal force. That should be in your notes, that there will be no problem in the future that involves friction that doesn't also involve you finding the normal force. So the moment they say coefficient of friction, you need the normal force. All right. So I actually only need to worry about this relationship and this relationship. I've reached the end of what Newton's laws can tell me. Any questions about getting to here? Because I'm going to do something different than I've done in the past. Let's put you over there. Well, I'm going to grab the two relationships that have acceleration in them, and I'm going to stack them. I have tension minus M1G equals M1A. Put another equal sign here. I have M2A, and I also have M2G sine theta minus tension. Those are the two distinct but important relationships because they are linked. It might be hard to recognize how they're linked because everything looks like a variable to you. But we were given the angle and we were given each of the masses. In general, most of the work we tend to do is to find out how our system behaves based on those masses. So we're going to be trying to eliminate tension. And that's the first thing we're going to do here. You've been doing that largely through substitution. I'm going to stop you and say, you just add the equations together. You'll get a faster result. There's always going to be an equation that has t that's positive and t that's negative, if you've done a good job of linking the problems together with a common sign. And you could do this if you have 5 masses in a row. You just add all of the equations up. All the internal forces will cancel out. And you can do it in a single step as opposed to doing multiple substitutions. So I'm going to do it in a single step here. The t's are going to cancel. And on the right side, I will get M1A plus M2A. On the left side, I'm going to get M2G sine theta minus M1G. Now, this is where I would encourage you to pay very apt attention. I'm going to factor out the A. When I do that, I am left with something that has some profounder meaning, something that you could use in the future. This is every block on a ramp with a block hanging off the ramp problem, wrapped up in one. I have the force down the ramp that we've seen a lot with ramp questions. This is the weight down the ramp. This is the weight of the hanging block. They represent two competing forces. That's why one's positive and one's negative. One's trying to pull the system in one direction and one's trying to pull the system in the other direction. This represents the net force, the sum of the external forces on the system. You'll know you've done all of this right if you see the sum of all the masses. That's what I'm seeing that here, and that's purposeful. The sum of the masses means that I have the inertia of the system here. If you don't see every mass that moves in this list, you've made a mistake. If the mass is part of your system and is moving, it has to appear in this list. But this is the inertia of the system. And you'll know you've done your problem right if it appears there. And then finally, the acceleration. This is F equals ma. So when you work the problem out, if you don't ever see the sum of the entire mass of your system, you've done it wrong. You should be looking for it. It should be there. Now that's it. It does tell me a couple things though. This part right here, this determines whether the system goes in one direction or the other. If it's negative, then the block that's hanging is big enough to overcome the block on the ramp. If it's positive, then the block on the ramp is big enough to overcome the block that's hanging. I don't know whether the answer is positive or negative. Now, if you put in the numbers I started with, the 40 and the 20 and the 37, you'll know. And I don't think we need to do that part of the problem. I think at this point, plugging in the numbers is the least interesting part. But they probably had two parts to this problem, didn't they? Did they ask about the tension? If they ask about the tension, then you will have to get a numerical answer here. And then to find the tension, you'll need to pick one of these. Is there anybody who would like me to complete the question with the numbers that I've selected? Going once, going twice. All righty. That is how this problem is done. And now we've done every one of those. So test on Thursday, sure, this will be there. With or without numbers, I haven't decided yet. And follow-up questions will sound like, what could I do to the mass that's hanging to make the system go the other direction? How would friction affect the system? Is there a world in which the system wouldn't move? Questions like that are important. And so I'll be asking you to discuss friction in a problem like this. I'll be asking you to talk about this, how would the system be into balance? You should know that the system getting into balance doesn't have to be about friction. This is when the system is in balance. If this condition is met, the system won't accelerate, right? When the two forces are equal. You should be able to make that decision. You should be able to come to that conclusion. Okay. That's problem number 4, talked into the ground. Next question. Yes, ma'am. Janessa? Yep. Number 6. Number 6. All right. There's a lot of ways to approach question number 6. And I'm going to start with one that's probably not what you guys would do. But question number 6 has the 3 sleds in a row. And excuse me for assigning it. It's kind of mean in that the math looks like hell. There's sled number 1. Let's see if I can do something fancy, like just copy it. Just go where I want you to go, you stupid fox. There you go. 3 of these stupid boxes. There we go. All right, 3 boxes, and they're all connected by little things there, and they're being pulled up a ramp with a tension force of T. And let's see, this one's M1, M2, and M3. We largely just did this question. So a lot of the things that we just did, we get to reuse. And I'm sure there's lots of things that it's going to ask. This is a train question, and not a particularly interesting one, except that it's on a ramp. But the answer looks like a mess. So for those of you who have worked the problem out, you know what I'm talking about. It's got to be a mess. And then you've got to figure out a way to get that into mastering. So this problem is unlikely to be on your test in a form like this. 2 boxes is enough for me to know if you know what you're doing. 3 boxes is a little excessive. If I was going to have 3 boxes, it probably wouldn't be on a ramp. I'd probably put it on a horizontal surface. Or I'd put the 3 boxes on a horizontal surface with the one hanging off or something like that. But I don't need all of this for you guys. But for homework, sure, why not? It's in the book. The first thing I would consider doing is not doing the problem like this. The first question probably is, what's the acceleration of the system? So if I was faced with having to do the acceleration of the system, I would, for that portion of the problem, just say that's one big box. So there, one big box. And try and get it down there without the program yelling at me too much. There, one big box. And what's the mass of this box? Well, it's all of the masses. So M1 plus M2 plus M3. There, one big box. There's no reason not to do it this way. There's no friction. There's no other forces acting in some way on the system that's going to cause one of these boxes to experience the forces differently than the others. All the boxes are on the same ramp. So you can do that. The tension force doesn't know it's pulling 3 individual sleds. It just thinks it's pulling one sled. And they allowed us to do this because they said that the things connecting the boxes together don't have mass and there's no friction. So this is just fine. And even if there was friction, if the friction is the same on all of them, it would affect them all the same. So I think this is the good way to go. Now, if you don't want to do it this way, we can break it up into lots of little sleds. But this is the fastest way to get to the answer. So to do it this way, I've got weight downwards, normal force perpendicular to the ramp, and tension up the ramp. And I'm going to try and exaggerate the size of the tension to indicate that the boxes are being pulled up the ramp. So I've got a free body diagram that is not really labeled, but I should label it all. So there, and this is M1 plus M2 plus M3 all times G. All right, so now I need a coordinate system to work on the problem. So I'm going to choose a coordinate system lined up with the ramp. There's the negative Y direction. There's the negative X direction. I'm going to recognize that this is theta. I'm going to draw in a set of components. And it's getting pretty small down there, but the only component that matters is this one, which is going to be M1 plus M2 plus M3 times G sine theta. Any question about what I've written here yet? All right. Net force equals MA. The system is accelerating, and I'm really only interested in the X direction. So tension minus M1 plus M2 plus M3 G sine theta equals M1 plus M2 plus M3 times A. That's it. That's the acceleration. I have all of the mass here, which is what I would expect to see. I have 2 competing forces acting to decide whether the system goes up or down the ramp. If the tension is greater than the component of the weight, it goes up the ramp. If the tension is less than the component of the weight, it goes down the ramp. And I've got my acceleration. So you have to solve that for A and type it all into mastering. Good luck with that part. There's probably more to this question, but is there any problem with what we've done so far? All right. Now the rest of this question is just going to be punishing, I'm sure. It's probably going to ask me like, what is the tension between some of them, right? Yep. All right. That's no we can do but to go through it, I guess. So I'm pretty sure it asked for the tension on all of them. So now, quite frankly, we gotta take away this box and break it up into little boxes again. I can't get this box by itself. Sorry. But you know it's 3 boxes. Well, there's one of them. How long do you want to watch Mr. Shelton screw around with his iPad program? I'd say the answer is probably not very long. Come on, be my friend here. There. It won't let me do what I want to do. There, that's better. All right. All right, so there we go. All right, so what do we need? Do we need the tension here or the tension here? Which one? Both? All right, I'm gonna do the bottom one first, this one. So let's do that one first. Because all 3 boxes have the same acceleration, and that acceleration is gonna be t minus m1 plus m2 plus m3 g sine theta all over m1 plus m2 plus m3. That's the acceleration. So if I look at just box 3 has its own little tension acting upwards on it. I'll call that T3. And it's got its own little weight acting downwards on it. M3G sine theta. I'm not going to free body it. It's the exact same free body diagram, just acting on one box, not all 3 boxes. And that has to equal M3A. Except this is A. So I got to plug all that garbage in. Now, I know, but yeah, Mr. Shelton, that's the part I need help with because, well, that's just algebra. And yeah, I get that you don't like the algebra. I get that it makes you a little crazy, but it is just algebra. And maybe you need tips and tricks to make your algebra better because you tried to input this into mastering 2 or 3 times last night, and it finally said you can't do it anymore because you're not very good at algebra. It might have even given you really, really bad hints on what you were doing wrong. Okay. I mean, I feel bad, but I don't. You need T3 by itself. So you put it on the other side. And so you get, T3 equals, what would I do here? So you do need to combine this a little bit. So did you try typing that into mastering and it didn't work? Got to work the system here. So let's see if we can't figure out how mastering did it. Okay. So I've kind of got a lot going on this page. Are we all okay if I go to like another page? So let's see what math magic they want us to do. So I've got this kind of mess, but if you look closely, there might be some things that we could cancel out that we haven't done yet. I forgot something from the other page. Can you tell me what it is? Yeah, M3. So let's deal with the fact that this is a fraction And because it's a fraction, I can separate the denominator and make it two separate fractions. So this one is m1 plus m2 plus m3. And this one is m1 plus m2 plus m3. Okay? Any question about that? So we all followed that okay? Well, that's the big thing. Cancel all of that with all of that. And now let's rewrite m3g sine theta plus, let's go ahead and put the m3 inside there. So I'll have m3t over m1 plus m2 plus m3 minus, since I canceled all that out, I just have m3g sine theta. So the answer is m3t over m1 plus m2 plus m3. So yeah, my answer doesn't have sine in it. It's algebra. It's not physics. But I can see how it would be sucky to do, you know, while you got the TV running and you're doing it late at night because you hate your physics. Yeah, I can see that. That's T3. I bet something similar happens when you try to do the other one. So I think I'm going to leave that to you guys and let you bang out that second one. It's going to be similar. You now have T3 though. Make sure that you subtract it. That second box has T3 in this direction and M2G sine theta and T2 in that direction. Make sure you use all the forces that are acting. All right, that was fun. I enjoyed that one. Any other homework questions? Let's see, I got 1, 2, 3. So Rachel, you had your hand up first. I've been putting her off for the last two problems, but don't worry. Go ahead. She wants number 1. What do you guys want in the back? 1 and 8. Okay. But this is quiz time. Number 1. That paper, just save it for first thing tomorrow morning. I'm okay doing homework. Number 1. Marcia. Is that it? Marcia's pushing down. Marcia. What? All right, so is that the problem? All right, so again, I'm going to do the problem for everybody instead of for you. So it's got a mass of M, an angle of, I don't know or care, theta, a force F, and coefficient of friction mu. And what kind of friction are we talking about here? Kinetic friction, so it's sliding. I think it's the takeaway here. Does it tell us anything about the way it's sliding? The box slides at constant velocity. There we go. Net force is 0. All right. I don't really care what the question is. There's only one possible thing they can ask us to do, and that's probably find the size of the pushing force or the angle or some garbage like that. So let's consider all the forces acting in the system. I'm going to have the weight of the box downwards, mg. I've got this pushing force that's acting like something like that. I don't know how big it should be, but I'm going to put theta here. So any problem with where the theta goes? All righty. I'm going to have friction, and I'm going to make the frictional force, this long, because net force is supposed to be 0. So I need whatever part of this is going to the right, have an equal part going to the left, and yes, I'm looking for this on the next test. Recognition that net force is 0 means balance. So whatever amount you got going one direction, you should have an equal amount going the other direction. And I see a combination of this amount and this amount. So I'm thinking my normal force needs to be pretty big. We're pushing this into the ground. We are creating a larger normal force than there is weight. So coordinate system, let's go with this direction to be the positive x direction. And I will have two components. I'll have a component like this and a component like that. I'm going to do a little fancy calculus here. No, it's just trig. F cosine theta there and F sine theta there. All right, that's my free body diagram and my coordinate system and breaking my off-axis force into components. Any questions till I get to this part? All right, moving on. Net force in the x direction equals 0. So I have two forces in the x direction. F cosine theta minus friction equals 0. Net force in the y direction equals 0. And I have normal minus F sine theta minus mg equals 0. So they tell me that the frictional force is proportional to the normal force. They gave me the percentage. My problem, it's 70%, but I'm just going to put a placeholder here for my percentage. These problems require an additional step. You have to pass the normal force through this function to get your frictional force. So there's not too much of excitement going on here, but remember, it's just saying that the friction is a percentage of the normal, which means you're going to need the normal force, which is F sine theta plus mg. Multiply both sides by mu, and I get mu n equals mu times F sine theta plus mg. This is now the frictional force. Questions about that? I know you can use numbers. I'm just not. I'm doing everybody's homework question. So substitute. So I get F cosine theta minus mu F sine theta minus mu mg equals 0. So that's it. That's all the physics can do for me. The physics got me two custom equations. I combined them using friction, and now I'm done. I don't know what the problem asks, but I bet I can find the answer from what I have found. So let's see. What does the problem want? Part A, check all that applies, whatever. Part B, determine the magnitude of the force. So I want to get F by itself. Okay, F by itself. So fancy algebra here. There. And let's see. Let's get this guy away from the others because he doesn't play nice with his friends. There. And then by itself. There's the answer, whatever that is. So whatever angle you got for the problem, whatever mu you got, whatever m you got, there's the answer. A couple of things I will point out, though, is that you're getting this m here, mu mg, that's pretty common to see in these questions. Notice the denominator has no units at all. It's cosines and sines. They don't have units. So my unit is going to be whatever mg is, because mu is just percentage. And that's going to be in newtons. So I feel pretty confident in my math. Is there more to this question? Go back and determine the frictional force. Okay, yeah. Once you get this, you've got the rest. Determine the normal force. So you good? All right. So number 8. Number 8. So I haven't heard one peep out of the people at home, so I figure they're asleep. All right, this is more of a motion problem than it is a, oops, don't want to do that. This is more of a motion problem than it is a force problem. But I put it in there because I don't think there's anything unreasonable about this. So I don't really know what the question asks, except that I've got this, and I've got, I mean, it's a child on a sled, but I mean, we're really just dealing with the box. The reason why it's here, because it's an inclined plane problem with a coefficient of friction. You should be able to do and combine those things together. Although they go on to ask you questions about, how fast it's going at the bottom of the hill, you can't do that problem with forces. Forces, though, can give you the acceleration. So you need to look far enough in the future to know that this is a motion problem with a force part to it. The only thing the force part can give you is that. But they tell you how long the slope is, so they give you this number. They tell you that it starts from rest. That's 3 pieces once you get the acceleration. And they want how fast it's going at the bottom. So, and I'm trying to give you the future of this problem because we're going to run out of time. There's weight, normal, and friction. I am betting that the friction is less than the weight down the ramp and that the system is going to get faster and faster as it goes down the ramp. So that's why I'm kind of drawing it this way. We've done this a little bit already today, so I don't feel like I can, I'm hurting anybody by saying that the part of this down the ramp is mg sine theta, and the part of this into the ramp is mg cosine theta. I'm going to state that the net force in the x direction equals ma, and that there are 2, mg sine theta minus friction equals ma. Any question about that? Because that's pretty standard. Only thing that's a little weird here, you need the normal force, which has got to be mg cosine theta. All right, it's balanced in the y direction. So whatever this is has to equal whatever that is. So I'm going to say to you that the friction is going to be mu times the normal force, which is mu mg cosine theta. Every single inclined plane pressure problem that we've had has looked like this, except now, you've got to add that little part for the friction. So I get mg sine theta minus mu mg cosine theta equals ma. Bye-bye, m. Gone. So you get g sine theta minus mu cosine theta equals a. That's a number. Plug it in, find out how fast you're going. That's part A. Any questions about part A? For those of you who need it, part B, the sled is here. Friction is this way. Normal is this way. Weight is this way. It's not on the ramp anymore. So friction is just going to equal ma, and it's negative still. And normal equals mg. So the frictional force got bigger because it's not on the ramp. All right. First 10 minutes of class tomorrow. Come with your practice test, but you're going to perform for me for the first 10 minutes. All right, guys. Have a nice day. If you want to know what's on your practice test, you've kind of done it here in homework.